Okay, welcome back to 16A. Today we're going to talk about a bunch of things. We're going to pick up from eigenvalues, eigenspaces, eigenvectors where we left off last time, but we're also going to talk about change of bases and transformations a little bit more, which is why I thought this video is a cool one for the day. In terms of reminders, remember that your homework is due Friday. Homework is the best way to prepare for the upcoming midterm, which is October 1st. I'm sure all of you already know this. There's practice problems that we have included on this homework. There's a problem about Alice communicating to Bob. There have been practice problems on previous homeworks. Of course, there's the actual homework problems. The reason we include practice problems is so that you can get a flavor of what kind of problems are going to be on the midterm, so that you're not surprised. So there's a reason that we include the practice problems in order to prepare for the midterm. Please try to do the practice problems. This will help you. I've gotten a lot of questions about, what's the best way to prepare for the midterm? The best way to prepare for the midterm is to do all of the homework, make sure you understand all of the solutions, do all of the practice problems. If you don't understand stuff, come to office hours. I have office hours after class every day. There's a stack of other office hours throughout the week. Please attend them. Another reminder to everyone, please, laptops and tech off unless you have an exception. It is far enough into the semester that I should not have to remind people about this. Thank you. Okay. So let's start right away with an example for a system that we want to try and understand. So we studied our favorite system last time, which was two states. But I want to try a little bit more involved system today. So let's try and think about a system, again, with two states. You can think of this as a PageRank example where, people are traveling to and from different websites to each other, and you're trying to figure out what is the steady state, or you're trying to figure out, after a lot of people have done a lot of jumping back and forth, what is the distribution of people in each of the different states. Here I want to think about, let's say we have website A and website B, and let's say 1/4 of the time, so maybe 1 in 4 of the links on this page A go to page B, and 3 in 4 of the links go back from A to A. And let's say half of the links on B go back to B, and half of the links on B go to A. So let's write out the transition matrix for this. This should take not very long, so this is 3/4, 1/4, 1/2, 1/2, right? And we want to try and understand, what is the steady state of the system? After time has gone on for a very, very long time, how are we going to find out what fraction of people are on website A and what fraction of the people are on website B? So, how many people remember what we talked about in lecture last time, where we had eigenvalues and eigenvectors, and we tried to figure out the steady state using eigenvalues and eigenvectors? People remember? So, why don't you take a minute and go through and calculate the eigenvalues for this particular matrix. Talk to your neighbor. You did a bunch in section last time as well. So make sure you understand how to calculate the eigenvalues for this. Make sure your neighbors also know. If they don't know, teach them. If you don't know, ask them. How many people are done? I'm not going to call on you. How many people need another minute? Okay, 1 more minute. Okay, how many people are done? How many people need another minute? Okay. How many people have taught their neighbor something? Or how many people have learned something from their neighbor? Either way. Good. So let's start by doing it together. What is the first step? Does someone want to call it out? What was the first thing you did? You wrote down a matrix, right? So if lambda is an eigenvalue, how do we find lambda? We consider the matrix Q minus lambda times I, right? What is Q minus lambda times I? This is 3/4 minus lambda, 1/4, 1/4, 1/2 minus lambda. Right? And then what do we try to do? We find the determinant, right? And why do we find the determinant? Because we want to find the null space of this matrix, right? We know that the eigenspace corresponding to eigenvalue lambda is the null space of Q minus lambda I. Right? And you may have heard in discussion last time the word eigenvector. And an eigenvector is basically going to be something that is an element of this eigenspace. Ideally, an eigenvector or a set of eigenvectors would be a basis for the eigenspace. Set. We will explore this a little bit more, and I'll show you exactly what I mean when I say this in the course of this example. But we have this guy, and we saw last time in lecture how we wanted to compute this. So we say, let's look at the determinant of Q minus lambda I. And this is equal to 3/4 minus lambda times 1/2 minus lambda minus 1/2 times 1/4, right? AD minus BC. Everyone see that? Okay, so what is this equal to? I got 3/8 plus lambda squared minus 5/4 lambda minus 1/8, which is equal to lambda squared minus 5/4 lambda minus 1/4. How many people got the same characteristic polynomial? Plus 1/4. Thank you. Plus 1/4. Really? All these people got the same characteristic polynomial? Plus 1/4, right? And so now, what does this give us as the factors of this? This is equal to lambda minus 1 times lambda minus 1/4. Right? So the roots of the characteristic polynomial are now lambda equal to 1 and lambda equal to 1/4. Right? Okay, so now I know that I have my eigenvalues, lambda 1 equal to 1 and lambda 2 is equal to 1/4. So how am I going to find the eigenvectors corresponding to this? Right? So now I have q minus 1 times I, which is basically 3/4 minus 1, which is minus 1/4, 1/2, 1/4, and 1/2 minus 1, which is negative 1/2. And I want to find the null space of this guy. So I'm just going to do Gaussian elimination. This gives me minus 1/4, 1/2, 0, 0, 0, 0, 0. Right? And so when I look at this row, I can just, again, I can multiply it, let's say, by 4. I get minus 1, 2, 0, 0, 0, 0. So what do I get as the relationship between my two components? I get minus x1 plus 2x2 equal to 0. So I get 2x2 equal to x1. And so what is the null space of this? I can write it as the span of a vector, right? Everyone with me? What is the span of the vector? What is the vector that I want to write there? 2, 1. Everyone with me? So this is the first eigenvector. And this is the eigenvector corresponding to lambda 1. So this whole space is called the eigenspace. And this guy is called an eigenvector. So I'm saying let's call this an eigenvector, but can I also write this as span of, let's say, 4, 2? I can, right? So is 4, 2 also an eigenvector? It is also an eigenvector. So the word eigenvector is often used in a way to indicate, like it feels like there should be only one eigenvector. But this is really why we're introducing this notion of eigenspace. Because if you think about it, any vector that is spanned by this set, spanned by 2, 1, will also have this property that when it is multiplied by this matrix Q, what you get back is just a multiple of this vector. So you will always have this property here, QV is equal to lambda V, for any V in this span. Okay? So sometimes you will end up in situations where you might have more than one eigenvector corresponding to a particular eigenvalue. You're not going to really see that happening so much in this class. So don't worry about it too much if we will explicitly talk about how to find these things. But just know that it is possible, right, that your null space for a certain matrix will be spanned not just by one vector, but will be spanned by two vectors, right? You've seen two-dimensional null spaces before. So if you have two-dimensional null spaces, that means that you might have two basis vectors corresponding to that eigenspace. And so you will have two distinct vectors whose linear combinations can actually lead to an eigenspace for that eigenvalue. Okay, so let's think now about the second eigenvalue. What is the second eigenvalue here? Second eigenvalue, lambda 2 is equal to 1/4. So since lambda 2 is equal to 1/4, what is q minus 1/4 I? Can people call it out? What is this matrix? One half, 1/2, 1/4, 1/4, right? And so if I want to now find the null space of this guy, I get 1/2, 1/2, 0, 0. And so the null space is basically the span of -1, 1. Right? Here I get basically x1 plus x2 is equal to 0. Did everyone get the same span? Everyone with me? Any questions? This is important to understand how to compute an eigenvalue and an eigenvector. So I want to really make sure I did another example in class, even though we've done one before. Yeah, question? If I scale, so the question is, what happens if I scale the initial matrix? So if I scale the initial matrix, that's a different matrix. Right? So I will compute the eigenvalues and eigenvectors for that. Because it's a scaled version, what you'll see is that the eigenvectors will remain the same, but the magnitude, the eigenvalues might change. Yeah? It depends on how exactly you scale the matrix, right? So you might have seen in discussion a question about determinants, right? And you saw that how the determinant scales when you multiply a certain row by a certain constant. So it depends. If you scale the entire matrix versus you scale an entire row, these are things that you can really try and understand. And these scaling properties, if you really want to understand well, there's an axiomatic way to derive a meaning for a determinant and eigenvectors, eigenvalues, how this scaling happens. You can go into this in much more detail in a class like Math 110. Here we're going to talk about it in a simpler setting. There's another question. Yeah. When I solve it for the eigenvalues, right, I set the determinant to 0. So that is exactly what we derived in lecture on Tuesday. So I can answer that question in detail after class in office hours, but I don't want to go into full details on that right now. The short answer is that we know that we can find we know that this determinant, where did this go? Yeah. This matrix Q minus lambda I is going to have a null space when the determinant of this guy is 0. And we want to find vectors in that null space. So we want to find lambdas such that Q minus lambda I has a null space, and for that we find the determinant. And if you go through and look at Tuesday's lecture, this is all derived there. Other questions? Yeah? If you're asked to find one eigenvector, you can just give me one eigenvector. If you're asked to find the eigenspace, then you should write the span of the vectors. To be safe, always write it out as a span. Because, you always want to remember that there's not just one vector. This entire space of vectors has that same property. Yeah. Great question. The question is, if the matrix has two eigenvalues, does that mean it has two eigenspaces? And the answer is yes. So it has one eigenspace associated with the first eigenvalue, and one eigenspace associated with the second value. So for example here, we're saying the eigenspace corresponding to eigenvalue lambda. So there's an eigenspace corresponding to value lambda 1, and an eigenspace corresponding to value lambda 2. Okay, last question.
Is there any physical interpretation of eigenspaces, eigenvectors, eigenvalues that kind of either corresponds to our physical interpretation of the determinant or of null spaces?
Is there any physical interpretation of eigenvalues, eigenvectors, eigenspaces? This is exactly what you will see in lab. There's also a question on the homework that will help you see this. There's many different physical interpretations, but one particular physical interpretation which talks about how the space is being scaled is exactly what you're going to see in the lab. You will see that by choosing to make a particular transformation, you can actually use the fact that eigenvalues of something are smaller than 1 to be able to attenuate the vectors that are being hit by that matrix. So go to lab. This is exactly the point of the lab. Hopefully it'll make sense once you do the lab. And there's a question on the homework that will also help you see exactly this. Okay. So great. So now we're here, and we have noticed now that there are two eigenspaces that we have for this matrix, right? And the two eigenspaces are spanned by the two eigenvectors. Let's call this V1 is equal to 2, 1, which we will call the first eigenvector. And, thank you. And we will call V2 is equal to -1, 1. Okay, so if I look at these two eigenvectors, is there something special that I can notice about them? In particular, I want to ask the question, are these a basis for R2? Thumbs up, thumbs down? Thumbs up, right? Why are they a basis? You can show that they're linearly independent. So 1, they are linearly independent. And 2, you can see that, well, any A and B, let's consider any A and B. Can you express any A and B, any vector, as a linear combination of V1 and V2? So what that means is that, can I find an X and a Y such that AB is a linear combination of these two vectors, right? So here I'm writing this basically V1, V2. You'll sometimes see this notation, right? You'll see this notation of stacked vectors. So when I stack vectors next to each other, I'm making a matrix of the columns of this, right? You've seen this in homework. If I stack vectors on top of each other, that means I can add them on top of each other. So if I was to put V1, V2, and stack them on top of each other, this vector would be equal to 2, 1, -1, 1. I'm not doing that right now. This guy, if I stack them next to each other, I get 2, 1, -1, 1. So you can use the stacking to create different vectors and matrices of different sizes. This is just a notation that you should know because you might see it some places. Okay, so now if I wanted to do this, and if I did Gaussian elimination on this system, what would I get? So this basically I have 2, -1, 1, 1. Oops, this should be a solid line, not a bracket. AB. Right? And then if I do further Gaussian elimination, I'm just going to swap these rows. 1, 1, B, A, 2, -1. And what this gives me is 1, 1, B, 0, -3, A, -2B. right? What I'm doing is I'm just taking 2 times row 1 and subtracting it from row 2. Doing it fast because you've seen this a bunch of times now. So now what does this give me? This gives me that y is equal to minus a minus 2b divided by 3. Right? And then what is x plus y is equal to b? I get this from the first row. So x is equal to y minus b, which is equal to x is equal to b minus y. Good, thank you. Which is equal to b right? Just algebra. So I get basically x and y are equal to a plus b by 3 and minus a minus 2b by 3. So now I can write this vector ab in terms of the coordinates of this second basis v1, v2. I can write it as a plus b over 3 times 2, 1 plus minus a minus 2b over 3 times minus 1, 1. I'll give you a minute to check my algebra. Everyone with me here? Yeah? Yeah?
So are we basically showing that the span of these two vectors?
Yes. Are we basically showing that the span of these two vectors is R2? Absolutely. Right? We want to show that V1, V2 is a basis for R2. And what are our conditions for basis? The first condition is we need to show that these guys are linearly independent. And second, we need to be able to make sure that any vector in the set that we're considering, so any vector in R2, since we're looking at a basis for R2, must be expressible as a linear combination of our vectors. So another way of saying that is saying that any vector in R2 is in the span of this V1 and V2. And so, in fact, we're actually doing that, and we actually computed what these values would be, right? So now that we have this, let's try and actually draw a picture out for what this V1, V2 looks like. And I want to use this to actually do a brief interlude on change of basis, and then we'll come back to eigenvalues and eigenvectors. So, change of basis. And you have a question on the homework that is like prepping you to basically do this kind of stuff. So, when we think about the standard basis, we think about the following, right? E1, E2. E1 is equal to 1, 0. E2 is equal to 0, 1. And now we have V1, which is 2, 1. And so 1, 2, 3, 1. So 2, 1 is the following. The span of this vector is the following line. So any point, remember, where did these vectors come from? These vectors came as the eigenvectors of Q, right? So any vector along this line is in the eigenspace of Q, corresponding to that eigenvalue. And we have V2 equal to minus 1, 1. So minus 1, 1 is the following. So this is V2. This is V1. Okay? And so what you just calculated here, what you just did was you said that if I can take any point here, AB, I can express it as a linear combination of this guy and this guy, which is what we always do, right? If I have AB, I know that the x-coordinate is A and the y-coordinate is B. But I can also express it as a linear combination of this guy and this guy. I can say, well, you go a little bit along this guy and then go a little bit in that direction. So when I say I want to express it as a linear combination, it's like if I wanted to get to this point, but I'm a robot who can only move in certain directions and I'm only allowed to walk along this direction, can I still get to this point? If I'm only allowed to walk along this direction, can I get to this point from the origin? If I can only walk along the pink line, can I get to this point from the origin? No. But if I was allowed to walk along the pink direction and the blue direction, can I get to this point from the origin? Right? I go kind of here, and then I zoom in that direction back to my point of interest. So we saw exactly how to compute this. And so now the question is, we know that these form a basis, and we want to try and understand how we can get back and forth from one set of bases to another set of bases. So we have our standard basis is E1, 1, 0, and E2 is equal to 0, 1. So the first thing I'm going to do is I'm just going to write out what happens to the vector 1, 0 in our new basis. Right? What happens to the vector 1, 0? So if we go back to what we just computed here, 1, 0 is A is 1 and B is 0, right? So I can write 1, 0 as basically 1/3 times 2, 1 plus minus 1/3 times minus 1, 1. Does everyone see that? I'm just using what we computed here. And I can write 0, 1 as 1/3 times 2, 1 plus 2/3 times minus 1, 1. And so if I was to write this out, I have basically this. I can write this out compactly as these two vectors go to 1/3, 1/3, minus 1/3, 2/3. Right? This 1/3 is the coordinate along, for E1 along V1, minus 1/3 is the coordinate for E1 along V2. These guys are called coordinates. So just keep this in mind. And now, let's really try to think about how to go back and forth between these two sets of bases. So let us say we know that A prime, B prime is a point in V1, V2. So what does that mean? So we just said that if we take this 1, 0 vector, it basically transforms to the vector 1/3 minus 1/3, right? So now, if I'm giving you a point in V1, V2 coordinates, which is 1/3 minus 1/3, how do I get back what that point was in the other set of bases? Is the question that we're asking clear? So if I know that A prime, B prime is a point in V1, V2, how do I figure out what the original, let's say, A and B were in our standard basis? So if I know that A prime, B prime is a point in V1, V2, I know that means that A prime, B prime are the coordinates of this point in V1, V2. So let's call this a vector, let's say V. So I know V is equal to A prime, B prime is equal to A prime is the coordinate along V1, so A prime V1 plus B prime V2. But can I write this as a matrix multiplying a vector? I have a linear combination of two vectors, right? I'm taking V1 and V2. These are two vectors. And I'm taking a linear combination of them, right? This is what the definition of coordinates means. So if I was to write this as a matrix vector multiplication, what would I write? What would be the columns of my matrix? V1, V2, right? So this is the same as V1, V2 times A prime, B prime. So if I call this matrix V, I get that. And so now, V maps a point in basis V1, V2 to E1, E2. What happens when I multiply both sides of this by V inverse? V inverse maps A prime, B prime. Oh, sorry. So this guy, let's say, is equal to AB. If I want to convert to the standard basis. In the standard basis, this is AB. In the change basis, this is A prime, B prime. And so now, if I multiply both sides of this by V inverse, I get basically A prime, B prime is equal to V inverse times AB. And so in our particular case, what is this matrix V? Can people see if I write here? So in our case, V is equal to 2, 1, minus 1, 1. So we're saying that 2, 1, minus 1, 1 times the coordinates of something in basis V prime gives us AB. So this is basis V1, V2. This is basis E1, E2. I feel like people are confused. Questions? Yeah. A prime, B prime, I'm thinking of as a generic point. So when I think of this point, right? When I think of this point as, let's say it's AB in our standard basis, it's AB in our standard E1, E2 basis. So that means that to get to AB, I had to walk A steps along E1. Oops. Thank you. AB is a generic point in our standard basis, right? What does that mean? To get to AB, I have to walk A steps along E1 and B steps along E2. Is that clear? But now I tell you, you can only move along V1 and V2. The question is, how many steps do you have to walk along V1 and how many steps do you have to walk along V2 to get to AB again? That is what it means to express AB in the coordinates of V1, V2. Does that make sense? What we're trying to do? So if I tell you that AB is what you would need to walk A steps along E1 and B steps along E2, then if you want to figure out how you would get to how many steps you would need to walk along V1 and V2, you would say, let's take this V inverse times AB. Is that clear to everyone? What we're trying to do? Yeah, question. That is what we're doing, yes. Yeah. So we're trying to go back and forth. We're basically trying. So remember when we were thinking of the pumps, the initial example when we started talking about invertibility? We're saying that, well, if I know where I am at x of t, I want to figure out what's happening at x of t plus 1. Or if I'm at x of t plus 1, I might want to know what happened at x of t. And I want to be able to go in the forward direction or in the backward direction. So if I start with a point in the standard basis, so if I start with a point in the standard basis, AB, if I tell you this, and you want to find a point, you want to find how much you need to go along V1 and V2, then you will use this equation. If you start with a point in V1, V2, and you want to figure out where it is in the standard basis, you will use this equation. Got it? Yeah. Write it out. I know it's really super confusing, but basically, this is exactly why I like writing this out this way. If V prime is a point in these coordinates, so then I know that V is A prime times V1 plus B prime times V2. It gives me basically this equation, right? That I have AB this V is equal to A prime times V1 plus B prime times V2. But this V, let's say, is also AB in our standard basis. So now all I'm saying is that this can be written as this matrix equation. Is that clear? Sorry, I can't hear you. V times the elementary matrix. So you can write it that way, right? But you would be using a different transformation. So exactly if you were to write it out as where did this go? Yeah, right here. So let me write this further. And let's say I know E1 is equal to 1/3 times 2/1 plus minus 1/3 times minus 1/1, and E2 is equal to 1/3 times 2/1 plus 2/3 times minus 1/1. So then I know E1, E2, if I stack these together, is equal to 1/3, 1/3, minus 1/3, 2/3 times V1, V2. This guy is V1, this guy is V2. This is exactly what we calculated here, right? And so now I get E1, E2. What is my E1, E2? 1, 0, 0, 1 is equal to 1/3, 1/3, minus 1/3, 2/3 times, what is this guy? We called this guy V, right? We called this guy V. V is what's written right here. Can you see this? There's no way for you to see all of this. Okay. V is just 2 minus 1, 1, 1. So this is V. And now, based on how we've written this, we derived this matrix by just calculating what E1 and E2 were, right? But what do we see about V and this other matrix? What is their product? What is this guy? Identity, right? So this guy must be V inverse. So this is something that is a little bit tricky. It can trip you up. Please be careful in writing it out. There's a homework problem that talks exactly about this. Read the notes and kind of practice going back and forth. Does this help clarify? Yeah? This guy if we call this guy V, this guy will be V inverse. But we're making the labels, right? So, yeah? We'll get there. Just hold it. Yeah. Volume. Yeah. How do we find those? So why did this become equal to the identity matrix? What is E1? E1 is 1, 0. I'm just stacking them together. Okay. So why did we want to do this change of basis business, right? So we're saying that basically we can go back and forth between representations in a certain basis and a different basis. And why did we want to do this? So remember, in the example that we started out at the beginning of class, we had this following pump system, right? And we found, how did we get these basis vectors? We found them by taking the eigenvalues and the eigenvectors of this Q guy. And we said that, here there's a nice steady state. For lambda equal to 1, we have this eigenvector, and for lambda equal to quarter, we have this eigenvector. And we said, lambda equal to 1 is the steady state, so this is the invariant vector. But what about this guy? What about what happens when we have actually the second eigenvalue? What is the importance of this? And so what we're going to see here is how transient and steady state vectors actually behave. So I know now I have my Q times V1 gives me lambda 1 times V1. In this case, lambda 1 is 1, so this is just V1. And I have Q times V2 gives me lambda 2 times V2, which is equal to 1/4 times V2. But what did we just find out about V1, V2? V1, V2 are a basis, right? We just saw that we can express any point in R2 as a linear combination of V1 and V2. So now can we use this to actually try and understand what happens when Q gets applied to some arbitrary vector? So let's say our initial states, right? We don't know what the initial states are. Let's say our initial states are represented by some x. Right? So that means that there's some x with, let's say, a, b. These a and b are not related to the a and b we did in the previous example. New example, new a and b. Is that clear? Please don't confuse this. Or should I use different notation, or is this clear? Everyone's okay? Okay. So if I take q times x, let's say q times x of t is equal to x of t plus 1. So I know that a and b can be written as some a prime times v1 plus some b prime times v2, right? I know that any point can be written as its coordinates in v1, v2. So if I want to try and figure out now what happens to q times x of t, I can write it as q times a prime v1 plus b prime v2, which is equal to a prime times q times v1 plus b prime times q times v2. This is just associativity, right? All I did was I bring the q inside, or distribution, both, I guess. Yes, question? What? xt, I'm saying that I can represent this in the basis v1, v2. I'm saying let's represent it in this basis. So let a prime and b prime, let a prime, b prime be the coordinates of x of t in basis v1, v2. Is that clear? Yeah? In the standard basis. No, x of t is in the standard basis. The coordinates in the v basis are a prime, b prime. So a, b are the coordinates in the standard basis. The coordinates in the v basis are a prime, b prime. Is that clear? Questions? Okay. So why am I doing this calculation? The point of this calculation is to show you why change of basis is useful, and to get to this question that was just asked is, how is this connected to eigenspaces and eigenvalues? And that's exactly what we're trying to get to. And there's another question about how does the scaling of eigenvalues matter? And that this is going to edge us in exactly that direction. So now we have this. Does everyone see how I got to here? So what is q times v1? Lambda 1 v1, right? A prime. But what is lambda 1? It's just 1. Plus b prime. Q times v2 is lambda 2 v2, which is 1/4 v2. Right? Is everyone with me? Okay. So now we have this. So basically, it's scaled a little bit along v1. We get some new coordinate along v2 as well. What about q squared times x of t? Q squared times x of t is just q times a prime v1 plus b prime 1/4 v2. Right? Q times x of t is this, so q times x of t is just this. Okay. So again, I can do the same thing. When q hits v1, what happens? I just get back v1. I get a prime times v1. When q hits v2, what happens? I get a factor of 1/4, right? So I have plus b prime times 1/4 squared v2. Okay, so now what happens if I have q to the t, or q to the, let's call it q to the m times x of t? What happens if I keep doing this m times? So what is this equal to? It's equal to keep operating the pumps. Once, twice, 3 times, 4 times. And we saw last time, right? When we kept operating the pumps, we ended up in some kind of steady state. We ended up with a vector that when it was hit by the pumps, it didn't change. Right? And we said that that vector was the same as the eigenvector corresponding to the eigenvalue 1. So now, what happens here? Can we write this out as a linear combination of v1 and v2, doing exactly what we've done so far? So what is this? A prime times v1 plus b prime times 1/4 to the m times v2, right? Does everyone see that? So as m goes to infinity, as m gets larger and larger, what is happening to this guy? He's going to 0, right? And so v2 is what is called transient. Because the eigenvalue corresponding to v2 is less than 1, it means that any component you have in the direction of v2, in this case in this direction, is going to keep decaying off to 0. whereas the component in this direction will remain. Which is why when I think about the steady state, I get that the steady state is basically this vector v1. Question? Yeah. Is it possible where you have a complex eigenvalue? Complex eigenvalues can happen. We're not talking about them today. Well, we might talk about them later in the class, but it depends on how much time we have. Yeah. Does it imply that the sum of the components is 0? No, it need not imply necessarily that the sum of the components is 0. Your eigenvectors need not necessarily have components that add up to 0. Maybe we can talk about it after class? Yeah. I want to get to some material, so I'm going to hold on questions for right now. So, okay. Let's actually jump to an example that you guys have seen before, which might also help make this more clear. So we saw this example last time. I'm not going to do it out again, but we had the Stanford website and the Berkeley website, right? And we had 1/2, 1/2, 1. Yes? If both, the question is what is happening if both of them are transient? Something is not being lost, but you're basically decaying off all of your components. Just hold on to these questions. We will get there, but let's make sure that first we all understand what happens with steady states. So if you remember from last time, for this problem, we had lambda 1 equal to 1 and lambda 2 equal to 1/2. And we had basically q minus 1/2. So here q is equal to 1/2, 0, 1/2, 1. And q minus 1/2 of I is basically 0, 0, 1/2, 1/2. And so the eigenspace corresponding to lambda 1 equal to 1 turns out to be the span of -1, 1. And the eigenspace corresponding to, lambda equal to 1/2. So last time in class, we didn't calculate this. I'm not going to do it out today because we don't have enough time. But believe me that if you were to compute the eigenvalues of this, you would get the following two eigenvalues. We computed the first one last time in class. And remember what we saw, right? If we kept running this system forever, where would all the people end up? They would all end up at Berkeley, right? And so when you look at the eigenvector corresponding to the eigenvalue 1, what do you see? It's saying that, there's no component at the first website. There's 0 here, and there's 1 here. So now, if I was to do the same thing as I did last time, and I said, okay, so now, do these two vectors span R2? Right? Let's call this V1. Let's call this V2. And now if I have Q times A prime V1 plus B prime V2, what do I get? I get Q times A prime times V1 plus Q times B prime times 1/2 times V2. Exactly what we did in the previous example. These are the two eigenvectors. I'm using the basis that is generated by the eigenvectors to express any point, right? I'm writing it in the basis of V1, V2. So now what happens if I take Q to the M times A prime V1 plus B prime V2? Yeah? Why are the Q's on the right side of... Oh, here. Here, why is the Q on the right side? Oh, good point. Very good, thank you. This was a typo. This Q should not be here. Really good, thank you. I made a mistake here. Did everyone catch that? So what happens if I take Q times... The first component is I get Q times A prime times V1. What do I get here? I'm just using the fact that Q times V1 is equal to V1. Q times V2 is equal to 1/2 V2. These Q's should not be here. So this is equal to intermediate step Q times A prime times V1 plus Q times B times V2. Does everyone see this? This is equal to this? Everyone with me? And does everyone see that this is equal to this? Sorry, this was a typo. Thank you for catching that. Because Q times V1 is just V1, and Q times V2 is just 1/2 V2. Got it? Sorry for the confusion caused by my typo. Okay. So now if I were to do this M times, what would I get out? We did this, right? We did this right here for the similar case. So what do we get out? So here I get basically A prime V1 plus 1/2 to the M times B prime V2. And if we write this out, this is A prime times 0, 1 plus 1/2 to the M, this is not a vector, times B times minus 1, 1. And now when M goes to infinity, what do we see? Which component is dying off? Right? The component corresponding to the eigenvalue smaller than 1 is going to die off, but the component corresponding to the eigenvalue 1 remains steady. And so the point of trying to introduce a notion of change of basis is basically to say that if I wanted to now understand, in terms of eigenvalues and eigenvectors, how a matrix Q transforms any point or any vector, I can use the basis of the eigenvectors to understand it. And all I need to figure out is, well, what is the eigenvector and what is the eigenvalue corresponding to it? Yeah. Question, why would we use the basis as the eigenvectors? Because when I use the basis of the eigenvectors, if I were to express this in some kind of different basis, right? If this, instead of V1, V2, I had E1, E2 here, which was not the basis vectors, then what would I get? I would get Q times A E1 plus B E2, right? But do I know any special property about Q times E1? Right? When I write this out, here I actually have to keep the Q on the other side. I just have to write A times Q times E1 plus B times Q times E2. Right? I can't do anything. I'm like, okay, I need to do some more algebra. But if I use this special basis, I have this special property of what happens when I do this matrix vector multiplication. Eigenvalues and eigenvectors are super special exactly for this reason, because we can use them to distill the impact of a matrix. So basically, what the eigenvalue and the eigenvector tells you is that if I look along one direction, for example, if I look along the direction of the first eigenvector, how much does my matrix transformation scale in that direction? That's the eigenvalue. If I look along the second eigenvector, how much does the matrix transformation scale in the other direction? Whereas if I were to look at it in some other basis, like the standard basis, I might not have that special property. So that's a good question. Do people see why this is not a good basis to express things in? Would we see that this would come out? We wouldn't have this special property, right? We wouldn't be able to write this equation. This is important. I really want to try and communicate this, because this forms the basis of a lot of ideas that you will learn in, say, machine learning optimization. When you go on to take classes like 127, 189, we will show you one application of why eigenvalues and the scaling of eigenvalues is important in lab. But when you go on to take these classes, you will come back to these concepts. And 16B will go into a much more detailed treatment of, how eigenvalues and eigenvectors behave, how matrix transformations actually scale your space. So, again, it was a great question. Why do we care about expressing things in the basis of eigenvalues and eigenvectors? This is why. Because it allows you to figure out which directions are going to die off and which directions are going to stick with you. Other questions? Yeah. Are you guaranteed to get n eigenvectors for an n by n matrix? Yes, but we will not go into proving this in this class, so don't worry about that. But yes. Short answer is yes. What is A prime, B prime in the context of the system? A prime and B prime are just the coordinates of a point, any point. Doesn't matter. Pick your favorite A prime, B prime. That's the point. They're parameters. I could write A prime, B prime equal to 2 and 3. It doesn't matter. So so if you choose initial values in A and B, let's say there's 5 people in A and 2 people in B, right? Then 5, 2 is the vector in the standard basis, E1, E2. This is a good question. Is everyone following? Let's say I had 5 people in here and 2 people in here. Then the initial state would be 5, 2 in the standard basis. However, what we would do is you would convert that 5, 2 into the eigenbasis of V1, V2 to figure out A prime and B prime. Is that clear to everyone? Okay. So, in the few minutes that I have left, I will do a partial answer to the question of the person who I think has now left. Of thinking about how many eigenvectors and eigenvalues we have. And we'll quickly prove the following theorem. For a 2 by 2 matrix, the eigenvectors corresponding to distinct eigenvalues form a basis. So we saw in these couple of examples that, we are getting this basis, but we want to show that actually you can actually form a basis for R2. And so let's say we're given that A V1 is equal to lambda 1 V1, and A V2 is equal to lambda 2 V2. So we somehow managed to find these eigenvalues and eigenvectors, lambda 1, lambda 2, V1, V2, for this matrix A, and we know that lambda 1 is not equal to lambda 2. Then we want to show that V1 and V2 are linearly independent, right? Because if they're linearly independent, then they're going to form a basis. So, want to show V1, V2 are linearly independent. So we're going to prove this by assuming something, assume the opposite, right? I'm going to say, if possible, let V1, V2 be linearly dependent. So, in this case, when I have only two vectors, V1 and V2, what does linearly dependent mean? Right? Linearly dependent just means that V1 is a scaled version of V2. So let's say let V1 is equal to alpha times V2. If possible, let this be true. If possible, let V1, V2 be linearly dependent. Okay. Take a minute to see if you can proceed from here on. Just talk to your neighbor for a minute. I don't want to do this too fast. I want to arrive at a contradiction. I want to say that, no, it's not possible for V1 and V2 to be linearly dependent. If I assume this, I'm going to, somehow contradict something. We only know two things, so it has to be using those two things somehow. It's not like we know that much else. I'll give you a hint. What happens if you consider A times V1? Can you write A times V1 as two different things? Using the two things you know about A times V1. So what is one thing we know about A times V1? One thing we know about A times V1 is that it is equal to, V1 is equal to alpha times V2, right? So this is equal to A times alpha V2. But what is A times alpha V2? What do we know from here? This is the same as alpha times lambda 2 times V2, right? Let's call this 1, 2, from 2. And what about A times V1 if we were to use 1? What does 1 imply about A times V1? This is equal to lambda 1 V1, right? So now we have this. What happens now if what happens now? Any suggestions on what to do? What happens if I substitute V1 here? I have lambda 1, let's call this star, times alpha times V2 from star. But what are these guys? Are these guys equal? So then what does that mean about these guys? This means that alpha times lambda 2 times V2 must be equal to lambda 1 times alpha times V2. But is this possible? Nope. Right? Not possible, since lambda 1 is not equal to lambda 2. And one thing I should have said, alpha is not equal to 0, right? This is not a trivial scaling, which means that I can actually cancel these two alphas on both the sides. Which gives me a contradiction, which implies that V1, V2 are linearly independent. So basically all these examples where we computed these bases is not any kind of coincidence. It's actually something that happens all the time when you have distinct eigenvalues. So with that, I'm out of time. Please come to office hours if you have questions, and I will see you on Tuesday.